Hello guys, so today I'll be solving this problem which is greatest sum divisible by 3. So the problem states that we have been given an integer array nums and we have to find the maximum possible sum of elements which is divisible by 3. So basically you have to pick up some elements such that the summation of them is divisible by 3. So yeah, so whenever you have this kind of a problem, so it's a pretty standard pick or not pick or not pick based problem, okay, which is a standard DP problem. So if you guys have solved like coin change kind of a problem, which you can find out in CSES problem state, problem statement, uh, yeah. So these two problems are or also this dice combinations. So all this kind of algorithms are based on this logic only, pick or not pick kind of algorithm. So yeah, this is a pretty DP algorithm because uh, when you look at this problem, the initial idea that will always come to your mind is, hey, I can build a recursive strategy so that for every element I can either pick it or not pick it, and with that I'll be doing all my calculation. And so something like this. So for example, let's say I have a1, a2, a3, an. Okay, so for the first element you can decide like, hey, I will pick it. Okay, or you can decide, hey, I will not pick it. So let's call it 5, you are not picking it anything. Okay, then for the second transition you will say, hey, I can pick a2 when I'm this state. Okay, this will give you a1 plus a2. Okay, or you can decide, let's not pick a2. Okay, then that will give you a1 only. Then from this state, if you are channelizing to a2, you can decide, hey, I will pick a2, or you can decide I will not pick a2. So yeah, like this you will grow exponentially. Okay, and you can see like for every state you are increasing by a factor of 2. So yeah, you will be having around like 2 to the power n, so you will be having, yeah, exactly 2 to the power n states, or 2 to the power n recursive calls. So yeah, this is the base idea you will be like initially getting when you see this kind of problem, which is okay, because from this intuition only you will get into the optimized version of this algorithm, where you will be involving some kind of a caching of solution, so where DP will come into play. So yeah, now why we cannot go with this, like we can go with this but we need to optimize this. Why we need to optimize this? Because here we have like 2 to the power n states, which will bring our time complexity to in the order of 2 to the power n, plus we will be needing some linear iteration and all that. So yeah, a factor of 2 to the power n will come into the picture, which will automatically give us a TLE state. And yeah, so basically from this state, like at the leaf level you will be comparing all the sum, you will be checking whether those sums are like divided, like divisible by 3. If they are, you will be storing only the max ones, and yeah, you will be finally returning the answer. But this will be a very slow process. Now in order to make it fast, you will be involving some kind of a caching mechanism. Okay, some kind of caching you will be doing, and that will automatically give you a DP approach. So yeah, now in order to solve this problem, okay, and in order to uh, help you out like how to cache out your answers, okay, so you need to think of states first. Okay, you need to define your state. Now what's your state should look like? Okay, now states are basically defined based on the inputs that are given from the problem. Now in this problem we have been given the array nums. Okay, so from this we can get an analogy like, hey, I have a feature of indices or the elements. Okay, now another state, like another feature we have, which is this, which is like from the statement itself, which is like divisible by 3. Now what does divisible by 3 means? It basically means whatever summation we are getting, okay, that summation modulus, okay, it should be equal to 0, okay. So this modulus factor comes into the play, okay. So mostly like this modulus 3 is another feature that we have, okay. Now if we look at our indices, so we have the range of 0 to n, okay. Now if you look at this modulus, its range is like 0, 1 and 2. So yeah, so if we do our whole state matrix, okay, it will look like, so let's say on the top I have indices, so here I will be having 0, 1, 2 up to n. I'll say why I'm considering n, I will explain that, but yeah. And here you will be having your modulus states or your modulus features 0, 1 and 2, and with this you will be having multiple states here, okay. And for each state you will be looking at their transition and you will be updating those answers. So yeah, so this is how our state will look like. So these are kind of the inputs for our state, or like the characteristic for our state, okay. Now our state will be a function of our indices and our modulus. So I can write it something like this. So state will be a function of indices and modulus. Cool. Now this is like we have defined based on the input features, we have defined a function. Now what does that function signify, or what does our state signify? Now we can like put a definition to our state, which is like our answer only, which is like my function should return the maximum sum, okay, that I can get from this two input, okay. Or I can say the maximum sum whose modulus will be this, okay. And let's say I have only traverse up to I index. So this is what I'm saying is like the standard definition of like the pick or not algorithm. So yeah, we have to consider the input parameters that we have, okay, and from that we have to define our state, and then we have to give a proper definition to our state, which is like maximum sum here. So yeah, now how it will help us. So if I simply say f of n, which is like I have traversed over all the elements, and I look at modulus of 0, what is the maximum sum? Then this state definition will basically tell me that what is the maximum sum when you have traversed all the elements and you have gotten the modulus of 0, which is nothing than the answer to our problem. So yeah, with this state definition we can directly get our answer. Cool. So we have set up our state. Now the next thing we have to look is transitions. Now in our pick or not pick algorithm, so there are two kind of transitions we are doing. So at every state we are saying whatever current element I have, okay, at my ith index, okay, I can either pick it or I will leave it, not pick. Cool. Now let's say in this state table only, let's say I want to find the answer for my this state, okay, which is none other than f of 2 comma 1. Cool. Now how can I arrive at this state? So the only way I can arrive it from my past states, right? Because I cannot because my future cannot impact my current state, right? So whatever past state I have, okay, there is some relation in between from which I can update my state. Okay, cool. Now, based on our definition, which is pick or not pick, okay, now let's look at our states. Let's look at our transition. So let's consider not picking up transition. So whatever element is in my second index, okay, if I'm not picking it up, okay, what all states should impact my current state? So I'll be having f of 1 1 as a candidate, or f of and f of 0 1 also as my candidate. Now I have these two candidate, but if I look at my state definition, which is maximum sum, okay, then if I look at f of 1 1, now if you think before answering f of 2 1, how did f of 1 1 got its answer? It must have gotten something from f of 0 1, just like f of 2 1 is getting from f of 1 1 and f of 0 1. Okay, so whatever value of f of 0 1 holds, okay, f of 1 1 by the definition of our state will always be uh, like greater than or equal to my f of 0 1 state, because when we will be when we would have updated this guy's value, we would have considered this state value. Okay, and since we are always storing the maximum sum, then whatever value this guy now has, it will always be greater than this. So we can easily neglect this value and we can only focus on this value, which is f of 1 1. So yeah, when we are not picking up an element, we will directly consider for f of 2 1 f of 1 1. Okay, so which is this state. Now let's make it in another color. Cool. Now when we are picking up elements, so when I'm picking up the element which is at my index 2, okay, so let's call it nums 2. Okay, so if I'm picking up this element, okay, and I need my final state to be 2 1, which is like my modulus should be 1. Okay, so I need to consider my current element's modulus also, because I need to find a state or a past state, okay, whose modulus when added up with this guy's modulus, okay, let's call that past state's modulus to be some x. Okay, when that past state modulus when added up this current element's modulus mod 3, okay, it should give me 1 as my final modulus. So I can do a hold here also, mod 3. So yeah, now what all values nums2 can give, okay, like or nums2 modulus 3 can give. So it can be 0, it can be 1, it can be 2. Okay, so if my current element's modulus is like modulus 3 is 0, and if I'm looking at my final modulus as 1, okay, then I should consider my past event or my some f of, let's say it's some dash, let's not decide upon I here. Okay, so here x should be 0. Okay, if I'm looking at my final state to be f of 2 1, okay, and I'm considering this guy's value. Okay, so if I do if I look at a past event or a past state whose modulus is 0, okay, and if I add up my current element value to that state, then I will arrive at f of 2 1. Similarly, if my current element's modulus is 1, okay, then I look at some past state whose modulus should be oh yeah, so here, yeah, if my current modulus is 0, okay, let's say if my current modulus is 0, let's consider this as m. Okay, so yeah, if current modulus is 0, then in order to get 1 here, I should look at a past state whose modulus value should be 1 here. Okay, similarly, if my modulus value is 1 here, okay, and if I am looking for my final modulus state will be 1, then I should look at some past state whose modulus state should be 0. Then only if I add up my current element with that state sum, okay, I'll get my final modulus state to be 1, which is to 1. So yeah, similarly the same argument goes for when my current element modulus is 2. So this x mod, so now it should be 2. So yeah, if my current element's modulus is 2 and I'm looking to make it 1, so I should add 2 here. Yeah, 2. Cool. Then only I can arrive at this state. Now, what should be this dashed? Okay. So here the candidates can be f of 0, 1, okay, or f of 1, 1, okay, or like this thing's for so yeah, if I'm going with this, okay, if my current element's modulus is 0, then here this can be f of 0, 1, or this can be f of 1, 1, okay. Now the same argument that we saw here when we are not picking up, if we only consider our like recent past event only, okay, because that guy holds the maximum value already, like based upon other past events, so I don't need to consider this state, okay. So whatever current state I am, okay, in that index, I will simply consider the -1 state of that, which is like 1. So yeah, so if I am picking up this element, okay, I should look at all my past state, okay, and their corresponding modulus, which is x here, based on my current numbers modulus, which is nums2. So yeah, this x definition is here. So yeah, so with that it may happen like whatever value I'm getting, so if I'm picking up this element, this value when added up with this guy's modulus can reach out to this state, similarly for this state, and this state can also act as a contributor for my current state. So yeah, so I think if I do a dry run, then it will be helpful for you guys. So let's do a dry run. Let's make some space. Okay, so let's consider one example. Let's say 4, 5, 6. Okay, let's say this is my array. Okay, and so yeah, let's say this is my array, and if I do the state matrix, okay, so I will also need to consider one 5 state. So why 5 state? Because in pick or not algorithm we consider a null state where we haven't picked up any element, okay, that's kind of my null state. So from that null state I start picking up element, and then or I decide like whether to continue with that state. So yeah, I will decide a null state, and and I will have my modular state here. So here I will say indices, and here I will say mod. So for modulus I have value 0, 1 and 2. Okay, cool. Now let's see, let's do this little bit of decoration, and let's go with this. Cool. Now when I haven't picked up any element, my sum is automatically 0, okay, which is like at this state only. So at that time, so with f of not picking up any indice and with 0 modulus, I will get a 0 value, 0. Now when I do not have an element, it is impossible to get a modulus of 1. Okay, similarly, when I do not have an element, it is impossible to get a modulus of 2. So I can put some heavy negative values here. Let's do minus infinity, minus infinity. Why minus infinity? If I initialize them with very small values, then later on I can maximize them. So yeah, let's erase this. Cool. Now let's try to find the value for this guy, which is f of, let's make it here, which is f of, or I can make it this. So yeah, f of, let's write our indices. So 1, 2, 3. So f of 1, comma 0. Cool. So what I will be doing, I need to maximize the sum, or whatever contribution I'm getting from my past event. Okay, I will be doing a like a maximization over that, and whatever value I get, I will put that. So I need to consider my transitions now. Now my first transition I will look, which is not pick. Okay, if I'm not picking up this guy, okay, so what state should I look? So if I'm not picking up this guy, I can directly look my past event, okay, which is like f of 0, 0, which is this. Okay, so I can directly put this value if I'm not considering this guy. Okay, now if I'm considering this 4, okay, I'll check the 4 modulus first, which is 4 mod 3, which is 1. So if I'm picking up this guy, okay, so this guy's modulus is 1. So which past state should I look, so that that state modulus plus this guy's modulus will give me 0. Okay, so if we check, okay, in order to get 0, I need to add 2 here with 1, so that when I add 2 with 1 and I do the final modulus calculation, it will be 0, which is this guy. So I need to consider f of 0, comma 2, and since I'm picking up this guy, I will be adding up this guy's value, which is 4. So let's erase this. Cool. Now let's do the max calculation, which is max of f of 0, 0, which is 0, and f of 0, 2, which is negative infinity plus 4. Now the max calculation will be 0. Cool. So I'll put a 0 here. Now let's look at f of 1, comma 1. So if I'm not picking up this guy, okay, then I can directly put this guy's value. So we have this f of 0, comma 1 as our candidate when I'm not picking up this element. Now if I'm picking up this element, so this element modulus is 1. So in order to get my final modulus as 1, I will be considering f of 0, 0, because this state's modulus, which is 0, when added up with my element's modulus, which is 1, their summation, which is 0 plus 1, their summation will resultant in my final state modulus, which is 1. So f of 0, 0, then I will be adding up this guy's value, which is 4. So my final calculation will be 0, 1, 0, 1, which is negative infinity, and f of 0, 0, which is 0 plus 4, and if I do the calculation, it will be 4. So I'll be putting up a 4 here. Cool. Now let's quickly do for 1, 2. So yeah, if I'm not picking up this element, I can directly put this guy, which is f of 0, comma 2. Now if I'm considering this guy, so in order to get my final modulus state to 2, so I need to consider this guy, which is f of 0, 1, okay, plus 4, because this guy's modulus, because my current guy's modulus is 1 and my this state modulus is 1, so when I add them up, okay, I'll get 2 as my final modulus. So yeah, so it will be max of 0, 2, which is negative infinity and f of 0 1, which is again negative infinity plus 4. Now we are getting an improvement which is like negative infinity plus 4, but yeah, it's not a big improvement, so I can still call it like negative infinity. So negative infinity. Cool. Now let's solve for this guy, which is f of 2 comma 0. Cool. Now if I'm not considering this guy, okay, so I can directly consider f of 1 0, okay, like as per the similar logic that we went through. But if I'm considering this guy, I will calculate this guy's modulus, which is 5 mod 3, which is 2. Okay, so in order to get my current state modulus to 0, I need to look at a past state whose modulus value is 1, because when I add up this guy's, okay, and f of 0 comma 1, okay, so this state value is 1 and my current guy's value is 2. Okay, so if I add up those modulus, okay, so 1 plus 2, it will give me 3. Okay, which when I do the modulus again, why I'm doing the modulus again, because in order to get it into the my modulus range, okay, I need to do this mod 3, which is 0. So yeah, I'll be arriving at this state because 3 is a multiple of 3 only, so yeah, its modulus will be 0. So yeah, f of 0 1, and I'll be considering this 5 here. So if I look at f of 0 1, oh sorry, there's a mistake. So I'll be considering f of 1 0 1 1, because yeah, earlier I picked 0 1, so it should be 1 1. So yeah, this will be max of f of 1 0, which is this, and f of 1 1, which is this 4. So 4 plus 5, so here the max calculation will give me 9, so I'll be putting a 9 here. Cool. Now let's quickly do this f of 2 comma 1. If I am not considering my current guy, then I'll directly pick up this guy, which is f of 1 1. Otherwise I need to consider this guy's modulus. Now I need to find another I need to find a past event whose state value when added up with 2 will give me 1. So that will be this here, f of 1 2, because if I add up my current guy's modulus 5, okay, this modulus is 2, then when I add up this 2, I will get 4, and yeah, the final modulus will be 1, because if you see, like 2 plus 2, which is 4, the final modulus calculation will be 1, so which is this. So if I do the calculation, which is max of f of 1 1, which is 4, f of 1 2, which is negative infinity plus 5, so here the max calculation will give me 4, so I'll be putting a 4 here. Cool. Then for this guy, which is f of 2 2, so if I do not consider this guy, then I can directly put up this answer, which is negative infinity, which is f of 1 comma 2. Okay, but if I'm considering this guy, in order to get my final state to 2, okay, I need to get f of 1 0, because my current guy's modulus is 2. When I add up 2 plus 0, I'll arrive at my current modulus state, which is 2. So I'll be doing 5 here. So I'll be saying max of f of 1 2, which is negative infinity, and f of 1 0, which is 0 plus 5. This will be 5. The max calculation will give me 5 here. Cool. Now we will look at f of 3 0. Now f of 3 0 is our answer, okay, because after this we have completed all our traversal, and as per our state logic, which should be somewhere here. Yeah, as per our state logic. So after we have traversed all the elements, and if the modulus values is 0, that will be my answer, because that sum modulus will be like that sum modulus 3 will be 0. Cool. So let's quickly find our answer. Cool. So if I'm not considering this guy, which is 6 here, okay, then I will directly pick up whatever value I'm getting in 20, which is f of 20. Okay. Otherwise, I'll consider picking up this value, and if I check this guy's modulus, which is 6 mod 3, which is 0. Okay. So in order to get my final state to 0, I need to consider f of 20. So I'll be doing 6 here. So if I do the max calculation, it will be f of 20, which is 9, and again f of 20, which is 9 plus this 6. So this will give me 15. So yeah, 15 is my answer. So if I look at 4, 5, 6 in this array, I need to consider all the elements so that I can get the maximum possible sum that is divisible by 3. So yeah, this is the logic behind the pick or not algorithm, and this is how we'll be implementing it. So now let's code it up. Okay. So yeah, let's increase the size a bit. I think yeah, this is enough. Cool. Let's quickly take the length of the nums. Now I will define my dp structure, which is int dp of n plus 1, and for the modular state I'll be capturing 3 states, which is 0, 1, 2. Cool. Now I'll be iterating over all my states, and now I need to define my state for my initial define values for my initial states, which I did here. Okay, so I'll be putting dp of 0 and 1 as negative infinity, or I can use int min here, and similarly for dp of 0, 2 int min. Cool. Now how we will do this? So first I will be calculating the modulus of my current element, so which is mod, and I'll be doing nums of I minus 1 mod 3. Okay. Now in order to do this efficiently, I will be iterating over all my modulus state. So I'll say m, let's keep it to j less than 3, j plus plus. Okay. Now when I'm adding up this modulus, okay, so what past event should I look? Okay, so in order to simplify our stuff, let's not calculate the past event, we can calculate in terms of future event. So if I add up this modulus with my current modulus state, okay, so let's call it next mod. So this will be j plus my elements modulus. Okay, and if I do this, okay, so this will give me the next modulus. Now I can update my, so from this element, okay, I can update a future value, which will be dp of, considering I, next mod. Okay, and I can do a max of dp of I minus 1 of my current modulus state plus my element, which is nums of I minus 1. Okay, this is when I'm picking up the element, like what I was doing here. Okay, now if I'm not picking the element, which then it will be dp of I minus 1 and whatever next mod I'm getting. So yeah, and finally I'll be returning dp of, I've traversed all the elements and I need to look for the 0 modulus. So yeah, all test is passed. Let's submit. So yeah, it got accepted. So what I'm doing it here is, so I'm basically iterating over all the state. Now for this current element, I don't, so in order to define my current state, okay, so I'm not defining it as dp of current I comma j, okay. Since I know my current element, okay, when added up with my current state or my current modulus state value, okay, that summation will give me some future modulus state, okay. I can directly update the answer here itself, which is like my next mod. So yeah, so this is kind of a reverse, or not reverse, so this kind of a future calculation I'm already doing it here. So yeah, now so if I look at the time complexity here, okay, so we are iterating over all the elements. Now for every element I'm doing three like my modulus state like transitions. So per element I'm doing 3, so that will be like 3 times n time complexity, okay, which is good because it is in the order of linear only. But if I look at my space complexity, I'm creating n plus 1, and for every n plus 1 rows I'm creating 3 columns, so it's 3 times n space complexity. But if I look at my transitions, okay, my transition only depends upon my past value, dpi minus 1, dpi minus 1. It's never going to be like I minus 2, I minus 3, because dpi minus 1 already carries the maximum value based on my I minus 2, I minus 3, all those state. So I only need to keep my previous state alive, okay, for my current dp calculation. So with that logic we can optimize our space, okay. So I don't need, so if for my ith state updation, okay, I only need my I minus 1th state values, okay. I don't need to consider I minus 2, I minus 3, because my I minus 1 is enough, okay, because it carries the maximum value. So yeah, I will discard all those this, and I will only consider this I minus 1. So in order to do that, I will reduce my dp space. So I'll say I can make it a 1D array, okay, and this I will call prev, and I don't need n plus 1. I will simply say 3, okay, and here dp of 0 will become prev, okay. So yeah, so basically I'll be, for every iteration I will only keep this guy alive, okay, because when we did all this calculation I was only look at my past events. When I was doing like this state calculation, I will only looking at this thing, okay. I was not looking at this guy at all, okay. I was only looking at my recent past event. So yeah, my prep will be that. So yeah, now here I need to define my current dp state. So current dp, so 3 comma 0. Cool. Now current is here, next mod is here. Now my dp of I will become my current, and whatever dp of I minus 1 I was doing, it will become pref. And once I have got the answer for my current dp state, I will update my pref with my current. Now at the end of all my iterations, okay, my pref will be updated with my final answer. So this dp of n, so my pref will automatically contain dp of n. So yeah, if I submit this, it works. And yeah, so the time complexity stays the same, but if I look at my space complexity now, I have reduced down this n factor completely. Now the only space I'm using is only a value of 3, okay. So it's big O of 3, which is constant space complexity. So yeah, now let's quickly do the same thing in Golang. So I'll say n len of nums I'll say dp, let's say two-dimensional matrix, int 0. Now let's um, update my dp. So I'm iterating over this. Dp, I'll say dp of idx, make 1D array. I can directly code the prev and current approach, like space optimized approach. So I can simply say prev is make of I need a 1D array 0 and prev of 1 will be some negative value. So I can consider negative this, because if I look at my problem statement, so my number varies between 1 to 10 to the power 4. So I think this will be maximum negative. So simply for same for prev of 2 I can do this, and let's consider this, or let's make it inf, and let's define inf as 1e4 plus 1, and and let's make it int. Cool. This is done. Now I'll be updating my answers. So traversing over all the states. So this will be I from 1, I less than equal to n, I plus plus, and here I'll be calculating the modulus of my current element, which is it's mod nums of I minus 1 modulus 3, and then I will be iterating over my modulus state, which is j 0, j less than 3, j plus plus, and I need my current dp state also, which is make of int 0, and so here I'll be calculating my next modulus. Okay, so which is my j plus mod 3, and I'll be doing dp of current of next mod equal to max of my current next I need to consider my previous jth mod and my current element's value, which is nums of I minus 1 when I'm picking up the element. Now when I'm not picking up the element, I need to consider prev of next mod. Cool. And finally, when I'm done with all this modulus state iteration, I'll be updating my prev with my curve, and in the end I'll be return prev of 0. Runtime. It says index out of range. Index out of range because I have done this. It should be 3. Same for prev, same for curve. Cool, it works. Let's submit. Cool. Now let's quickly do it for Rust. So let's capture the length of nums. This. Now let's create our dp array. So prev. Let new prev equal to vec of 0 and 3, and I will say prev of 1 as a very large negative value, which is I think in Rust I32. It has its own. Cool. So I'll say I32. It's a method. It's an attribute. This and prev of 2 equal to I32 min. Cool. Now I will iterate over all my rows, which is or my all my indices. So it will be I equal to I in range 1 to n, and then I need to calculate my current values modulus, which is mod. I cannot use mod because it's a reserved keyword in Rust for modules. So I'll say mod equal to nums of I minus 1 mod 3. Okay, then I need to consider yeah, I need to create my current DP, which is let mute cur is back of 0 3. Okay, then I need to iterate over all my modulus states, which is j in range of 0 to 3. Now I'll be updating my current DP, but yeah, before that I need to calculate my next mod. So let next mod, let's call it this, next mod equal to j plus mod plus modulus of what am I writing, 3 uh, 3. Cool. And I'll be updating my current with next mod, um, which is I need max, so I'll be using std comparator. I'll be saying max of my previous jth mod value plus my current elements value, which is nums of I minus 1, and I will compare it with, so this is for my picking up element, and I will compare it with when I'm not picking up the element, which is simply prev of next mod. Cool. And after that I'll be updating my prev to cur, and in the end I'll be returning prev of 0. Cool. Now let's look at my indices. So at this point, this guy is I32. I modded with this, so I need to convert it into usize as usize, and yeah, current is this. Now next mod, j is usize, mod is usize, so this guy will automatically be usize, so I can use this, use it as an index. Then yeah, should be good. Let's run this. Oh yeah, should work. Cool. So yeah, all three languages done, and yeah, this was the core algorithm behind this problem. Where is this? Yeah, pick or not pick. So but yeah, these are all my explanation, but I think you guys will get into like how this transitions are happening and how to think it yourself. It's only by when you solve a lot of like pick or not kind of algorithm problem. So I'll recommend solving this CSES problem set, maybe the initial 4 problems. So from that you will have an idea, like, because at every time when you look at a DP problem, you will always go into recursive approach. Okay, but in the end, like that will always give you TLE, so you need to uh, think of like how to convert into DP and which pattern to follow. So yeah, so this is like one of the pattern of pick or not, and this I used to solve this problem. But yeah, cool. So I hope you guys learned something new, and I hope I was able to explain you this problem. And if you like this video, please do subscribe to the channel, and you can post any comment if you like. So yeah, bye bye, stay tuned.